Okay, next we have Michael Sorochan Armstrong, who's coming from University of Granada and talking about time and frequency domain analysis of data.
Hi, everybody. Can you hear me? Yes, good. Okay. Well, if you can't, too bad. So my name is Michael Sorochan Armstrong. I'm a personality hire at the University of Granada Department of Computer Science. And today I'm going to be going over very briefly some of the time domain analysis we've been doing for GCxGC-TOF and MS data. But primarily I want to introduce the idea that it's time to maybe let go of the peak table for some of your analysis, because I think it causes us all a lot of grief. And if there's a convenient alternative that's similarly interpretable, I want you to open your hearts. So maybe for some people in the regulatory industry, you do need to know every single chemical component. But if you're looking for just the chemical components that differentiate, I would invite you to maybe look at the frequency domain. I gotta go quick, but again, thanks for having me. So again, just like we saw in the previous presentation, right, we have our sort of tensors, our raw data, and ultimately we want to put it through something, a black box, and hopefully the black box is the most parsimonious, most transparent possible thing we can get in order to get from the raw data to the peak table. And of course the challenges are, everybody knows that the chemical components can drift across the first and second dimension retention times, and we assume that the mass spectrum is invariant. Now, the trouble with this, when you're doing in the time domain, is that you're sort of squaring out these regions within which you expect peak drift to occur. So if one of your friends or supervisors sticks their fingers in the modulator and breaks the second dimension column, it's a great way to reconnect with your faith that the actual chemical components won't drift too much. So ultimately, we're looking at heterogeneous data analysis, because if it's homogeneous, if the column configuration is relatively consistent, then it should be good. And for this analysis, I'm going to be using Python, because I hate MATLAB. Some Python haters will say that Python is slow, but in fact, you can parallelize a lot of the tasks in a lower level language, like Python is most Python functions are actually written in C. So if you're using PyTorch, it's very similar to NumPy, but it can be distributed across GPUs, which is really nice, very fast. So the first thing when we're dealing with high resolution data is that we have to actually associate the masses together to do any sort of multilinear operations. So this is just a free, fun, and fast C code that me and Kort Sandel programmed, and it's available in NumPy. So if you want to just follow the QR code, just input your credit card information and your mother's maiden name, and it should be good to go. So again, I'm going to be doing time domain, deconvolution, and then I'm going to be doing frequency domain analysis, and then sort of this multivariate statistical analysis called the GLM. It's a generalization of ANOVA. And we're going to look at the factor matrices and see what we see. I don't like the time domain analysis. I'm very biased. I'm going to tell you this right away, because this looks more simple, more parsimonious on top. But with the region of interest selection, it's hard. With the deconvolution, it's hard. You have to pick numbers of components, thresholds, all kinds of ugly things that I don't think are beautiful. All of these things on the bottom are automatic, parameter-free. So you can fold and unfold data, GCxGC-TOF and MS data, a couple of ways. You can unfold it along the second dimension retention time, first dimension retention time. You can analyze it across both of these unfoldings using this algorithm. But this algorithm isn't stable if the regions of interest aren't square. So please read this paper, cite this paper. Together we can get my H factor up to 2. But just for the purposes of convenience, I'm going against my better judgment than just doing unfolded parafact 2. So here we have the component number selection for the time domain analysis. We do a leave one out cross-validation routine. This is a region of interest. We train it on all of the samples except the one we're testing, and we iterate through all of the samples. And then we pick the component number with the lowest error on the test set, right? We're not using all of the information. Obviously, you can do some sort of ANOVA type analysis to see which component numbers are significantly different from each other. But just for simplicity, we're just going to go with this. And it does bias towards higher component numbers, obviously, but you can see that it does get you what you're looking for, in addition to some extra super fun stuff called the noise components, which you can sort of see like here, here, and here. So it's still very noisy, but for components actually 5 and 2, you get good mass spectra, and you get good quantitative results. And then using the power of climate change, you can make this as fast or slow as you want on a server of your choosing. You take the high-res TOF data, you put it on the rod-to-table functionality, and then you can even access the Windows software such as the NIST library using a Docker image. This gets output to a file structure, and then you can query that using pandas or any kind of relational database, which is all included in the software that will be available sometime. Yes, climate change, horrible thing. So yeah, this is sort of what you get out. I did a really bad region of interest selection, but if you want a good region of interest selection, talk to the guy who's dressed like a finance major. His name's Ryland. But yeah, this is just a noisy region, but ultimately you can see we get the quantitative results, we get the F values, the P values, and the reverse library image search. Also, Paul Albert Schneider, who was a co-author in the previous presentation, he did this really big brain thing. And we published this article in the Journal of Chemometrics where we showed that the deconvolution algorithm I proposed isn't very good. But that's okay. That got my H impact up to 1. And you can see that unfolding the data, this was my contribution, unfolding the data for GCxGC-TOF MES data has an impact on the coupling matrix in the ParaFact2 model, and that makes it not ideal, unfolding the data for ParaFact2 analysis. So hopefully he's going to come to Granada, and we're going to implement this in the next release of the software, after the first release of the software. That hasn't happened yet. Okay, so topological data analysis, I don't like time domain analysis, so I was thinking if your friend does put their fingers into the modulator and breaks it, and now you have heterogeneous data, is there some sort of like nonlinear basis function that can associate two samples even if they don't have much to do with each other anymore? So the typical ones are UMAP t-SNE, they're slow, more meta parameters, more problems, non-unique solutions, wavelet transform, I don't like it, I don't want to pick a wavelet. Fourier analysis is great because it's agnostic to sort of like peak shape different deformities and whatever. The only difference is that when you're working in the complex domain, the linear algebra is a bit different. So I thought I'd test this out. Actually, the idea for this type of analysis was proposed at the last multidimensional chromatography conference. So we had this kind of silly idea. What if we have these abstract representations of the GCxGC-TOF MES data, right? So in the frequency domain, it doesn't make any sense just looking at it. That's a whole bunch of garbage. That's a whole bunch of garbage. But if you do the inverse transform, after calculating statistical significance for the factors you're interested in, say time, you can see it in this sort of ANOVA-like table right there, you can do the inverse transform on the factorized matrices, and you can see that in the raw data, you can see the peaks that are responsible for differentiating in the frequency domain. Now, I compared this with the peak table analysis, and the peak table analysis had a lot of zeros, but when you accounted for the zeros, this experimental data was consistent with the peak table analysis. So again, if you let go of the peak table, wonderful things can happen, but you have to be willing to let go of the peak table. If you're not willing, it's not going to happen. Okay, and just to convince you a little bit more, Gaussians can be represented by sums of sinusoidal components, so you're not going to get one frequency per one component necessarily, but you can represent several peaks as several different frequencies with offset and amplitude in the complex domain. And so when we do 2D FFT ASCA now we're looking at the imaginary and real components of the different M over Zs as we iterate through them. This is what we're operating on right here. And we fold this back into a tensor, and then we do this ANOVA-like analysis. The D is the design matrix. That's a sort of representation of ANOVA as a series of linear factors. So we find the factor that we're interested in. Let's say it's factor A. And then we do parafasca, or parafac. This is some nerdy stuff, but basically MATLAB is cringe, Python is based, and that just has to do with where the memory is indexed, how it's stored. But they do the same thing, just in different orders. So we published this paper about how to incorporate error information, so your residual tensor. You can look that up. It's a book chapter. Don't judge me. And you can visualize the uncertainty per experimental level. So if we're looking for peaks in our data that are significantly different from each other, that's really helpful to do. So when we're decomposing it in the frequency domain, across the different modalities, you can also incorporate error information if that's something you're interested in. And this is just super quickly the results. I don't have a lot of time, but these are the inverse loadings. I was hoping that by adding more components, I could actually get the peaks themselves, but because it incorporates spatial information as part of the imaginary component, so we actually get sort of chemical families with similar retention times in the first and second dimension, or sort of correlated retention times along the first and second dimension retention time. So this mass spectrum is kind of useless, but you know, you can zoom in on peaks that are significant and then extract the mass spectra that way. So this is truly heterogeneous data analysis, because in that paper I showed you that was recently published, we scrambled the peaks a whole bunch, ridiculous jitter levels, and we saw that the evidence for statistical significance was always significant. It didn't matter how far away the peaks were, which was really, really great. The only thing it suffered from was if there was peak inversion. So as long as you're using the same column set, if you took a sample like a year ago, 2 years ago, it doesn't matter, as long as the underlying topology of the data is the same. This is just a bonus slide, but I've been doing some work with interpolative transforms. So if the data is irregularly sampled, you can do what everyone did in 2016, where they put the smooth filter on their faces. I have a friend who did it with their baby for some reason. So the baby looked younger. Using the power of Bob Ross, I zeroed out this column bleed section, and I thought, why not interpolate the column bleed section? What if I wanted to quantify, oh man, you can't see it, I'm so sorry, folks. But there's this bleeding, this tailing peak, right? So it intersects with the column bleed, we get rid of the column bleed, we do the interpolative transform, now we can integrate the peak in the absence of the column bleed. I think that's kind of cool. Maybe it's a edge case or whatever, but I like it. Okay, so ultimately, this is heterogeneous data analysis. It opens the door for process control, interpolating irrelevant information, extrapolation for saturated masses, exploratory data analysis, statistical analysis. Imagine, if you will, someone uploads their data to this really, really cool server, and you could analyze your experimental data in the context of other people's experimental data, irregardless of differences in column configurations in the frequency domain. That's my dream. So if you're part of that dream, give me money. So I'd like to thank my supervisors, you know, Dr. Jose Camacho, Dr. Regino Zamora. I'd like to thank Angela Merkel for giving me money. I'd like to thank Pedro Pascal, President of Spain, for giving me money. Court and Grace from Chemistry Matters in Canada. And one of you can come home with a beautiful cat. He has FIV, so he can't play with my other 8 cats and a pigeon for different reasons. Anyways, thank you so much.